In this lecture, we are going to derive Nernst's equation. This is going to be a helpful tool in determining cell potentials when we're at non-standard conditions, like when we're not at 1 molar concentration for our electrolyte. So let's start by connecting free energy and equilibrium and cell potentials all together. So in voltaic cells, chemical energy is going to be converted into electrical energy. We're taking that potential energy difference and converting that into energy that's going to actually be able to do work. And so let's first start with electrical work. That's going to be the potential difference times that charge transferred. And so we're going to find that that actually equals, that electrical work is equal to the negative of NFE cell, which, what's that? So this N value right here is the, the number of moles of our electrons from our balanced equation that we have for our redox reaction. So moles of electrons from our balanced equation. So it's how many moles of electrons are transferred from our oxidizing agent to our reducing agent, or sorry, reducing agent to what's being reduced. And then F is Faraday's constant right here. That is the 9.648 times 10 to the 4th joules per volts per mole. And that's really the charge in coulombs of 1 mole of electrons converted into joules per volts per mole. And so these two together, N and F, equal actually charge essentially. And so, there we go. And so that this is helping us understand energy as this work, this maximal work performed versus overcharge relative to charge. And then we have the potential of our cell times that charge value. And that's going to give us the amount of electrical work that can be performed. So kind to free energy. Since we've already talked about free energy as being a way of measuring useful work that can be done, and electrical work falls into this category of useful work that isn't expansion work that's happening from a gas expanding out or contracting. So we're in a closed system. So that Gibbs free energy is going to equal the work that's exchanged by the system with its surroundings, not that pressure or that work from pressure force. And so it's going to be that electrical work that's happening if that's the only work being done. So that means if we can say that that change in Gibbs free energy is representative of the maximum amount of work that can be accomplished by the system, we could say under standard conditions and standard state that that change in free energy, the standard change in free energy, will be equal to that electrical work, which again is equal to the negative of the number of moles of electrons in our balanced equation times our charge of electrons per mole of electrons times that cell potential. And so now we have a way of relating free energy to our cell potential for these redox reactions. So let's play with some equations here. To the left-hand side of your screen, you should see a derivation. And to the right-hand side, it's the summary. I know for some of us, derivations really help make these equations make sense, and others we can get lost in the weeds and we're like, I need to be able to understand the equation as the sentence I am understanding it to be, not the journey to get there. So choose your own adventure, but I'll walk through this. So what we're doing here is we're taking two equations we already know about, that free energy connection to equilibrium constants that we talked about in our previous chapter, and then our new free energy connection to the cell potential. So we can rearrange and manipulate these two equations together, since they're both equal to standard free energy, to get a value that is our energy of our cells equal to our RT divided by NF times the natural log of K. And conventionally, we typically, for this equation, we work in log instead of natural log. And so our conversion for natural log to log of x is right here, that our natural log of x will be equal to 2.303 log of x. And so we're going to replace that natural log of x in the equation we just built from our two free energy equations for this 2.303 log of x. And the y of that, I don't have an answer for. Sorry. Combining this, we're going to get this big beast of an equation that sets our cell potential equal to, we have our R value, we have our temperature at room temperature, we have our moles of electrons from our balanced equation. We have Faraday's constant right here, and then we have the 2.303 log of our equilibrium constant. I'm going to combine all of those constants that aren't going to change, multiply, divide, and I'm going to get this value 0.0592. So we can simplify this equation just by multiplying out our constants and making them into one value. And so we get that the cell potential is going to be equal to that value divided by the moles of electrons in the reaction times the log of our equilibrium constant. And so this will allow us now to relate our equilibrium constant with our cell potential. So now we can connect, I'll show you right here, we can connect our free energy, our cell potential, or our equilibrium constant, and our cell potential together. We have a way of converting between all three of these. And all three of these values help us predict spontaneity of a reaction. So we know already that equilibrium constants that are larger than 1 and free energy less than 0 tend to lead to our spontaneous reactions. And now our cell potential, if that's greater than 0, we expect a spontaneous redox reaction. So we have these three kind of metrics that allow us to evaluate if a reaction will just happen or if we would have to apply, like put energy into the reaction to make it happen. We can also, I like this triangle just because it summarizes really well how to convert in between these three different values and the equations that you would need to be able to manipulate and use to solve problems with all three of these. We have our free energy and relationship to equilibrium constants. We have our free energy relationship to our cell potential, and we have our cell potential relationship to our equilibrium constant. So now let's build to the Nernst equation. So we're going to use, we're going to go back to our previous chapter when we talked about free energy. We talked about free energy at a standard state and non-standard states, and we had a way of calculating that. We would use that change in free energy for a system not at a standard state would be equal to an adjustment to the standard state free energy. So it'd be that standard free energy change plus our constant R times the temperature it was at, and then the natural log of Q. Remember, Q is equal to our concentration of our reactant, or products over our reactants with our coefficients as exponents. It's essentially our equilibrium constant when the system is not at equilibrium. All right, well, now that we have all of these equations that connect free energy to equilibrium to cell potential, we can substitute and rearrange. And so we're taking that equation that our free energy is equal to the negative of our moles of electrons in our balanced reaction times Faraday's constant times cell potential. That's this piece right here. And we're replacing that for our free energy. So we're substituting that in right here for these G values. And then we're dividing everything by the negative number of moles for the balanced reaction and Faraday's constant. And we can rearrange that into this equation that relates the cell potential at non-standard conditions to that standard cell potential minus RT divided by NF, natural log of our equilibrium, our reaction quotient, Q. Again, we're also going to take that natural log is 2.303 log of x and combine these two equations right here to get this large equation that has a lot of constants in it again. We're going to combine all of our constants and we're going to simplify, and we're going to end up with this equation that is the Nerst equation, that cell potential at non-standard state will be equal to the standard cell potential minus 0.0592 divided by the number of moles of electrons in our balanced reaction times the log of our reaction quotient. And now we can calculate those potentials at non-standard conditions, which is, you know, it's hard to just always be in the same standard condition experimentally. Here's an example problem. Give this a try on your own. I'll go over the solution in another video.